I'm Andreas Ronge, as he said, and I work as a consultant, and I've done a JRuby wrapper for the Neo4j graph database. And I think the Neo4j graph database is probably the most popular graph database around. So first, a very short introduction to different types of NoSQL databases. And up here in the corner here, we got this database that's extremely good at scaling. You can simply add more hardware and you get better performance. And we do that by using very simple data structures like distributed hash tables. And yeah, the consistency model is more relaxed also. But on the other side of that, you got databases much more capable of handling complexity and like semi-structured data or data that is highly connected. And we do that by using much richer data structures like the graph. But all of those database types were capable of really majority of the use cases we have today. So that's why I think we should instead focus on simplicity and or how to tackle complexity. That's the talk today. And one maybe naive approach, if you really want something simple and that works in production as well, skip the database. And yeah, what would that look like? Would that be a wonderful world, wouldn't it? Just have no dependencies to anything at all. So it's just ultimate programming happiness, I think. Of course, you would just use the features that the language support, data structures, encapsulation in object, and references between objects and data structures. And how do you query? You use what you have in the language, hash maps, or you just iterate through things. But of course, that's not enough. You need to have the data accessible from many different clients and persist on the disk. So we need somehow be able to persist objects, data structures, need to persist references. That's usually very tricky. And how about query? Do you have to use a new query language? Or what I really would like is to have expressive power of a language, because quite often when you go to a database, these beautiful things you have in the language just disappears. And the first thing that comes to mind is, of course, it's nothing new here. Object database has been around, I think, from the 80s or 90s that tries to solve this problem. But most of those databases were very coupled to you can only use it from one programming language, or maybe just one virtual machine. And maybe it's not a good idea to not have a clean separation of data and code, because usually the code is the most valuable, the data is the most valuable thing you have, and often outlives the application. Frameworks and language comes and goes, but the data will exist there. So how about using a graph? And you think about it, how the program works. It's in memory. It's really a graph. For example, references between objects, data structures, and to persist objects in a graph is quite a natural thing to do. And how about query? And this is what a graph database is really good at traversing relationships or references. You can do it extremely fast. And what I'm really talking about is impedance mismatch. The problem of using an object-oriented language and then using a database that you can't, there is no simple map of that data structure to the database. Okay, so I'm going to have a short introduction to graph databases, and I'm going to show what the Neo4j graph database look like. And it's actually very simple to use a graph database because it just consists of 3 building blocks. And that is nodes. We've got 2 nodes here. Relationship, we've got 1 relationship here. And properties. And both nodes and relationships can have property. And in Neo4j, relationships have both a type and a direction. So here we see that from Alice to Bob, there is a relationship going from Alice to Bob. And it is of type nose. Okay, but maybe it's easy to describe this, for me at least, with seeing a bit of code. And here what it looks like in the JRuby wrapper, but it's not very different in Java or Python. It's just 1 line of code to create those nodes. So here we create 2 nodes, and we have 1 property each. And then we connect those 2 nodes with a relationship, and the first argument is the type of a relationship, and the second is the from node, and the third one is the to node, and then we establish this relationship. And then relationships can also have properties, and properties, they have primitive values like strings, booleans, fixed num, and can also have arrays. Okay, question. How do we find things in a graph database? And one way of doing that is to simply traverse relationships. So here we traverse from the node A. We say we want to go outgoing relationship, and we tell which type of relationship. And this returns in the Java library, it's iterator. And in Ruby, it can simply wrap that as a Ruby enumerable, and then you have access to all the Ruby methods. So you can just find things like you'd normally do in the language. And you can go both ways. If you want to go our way from B, you can find A by navigating incoming relationship. And that's really what the graph database is all about. But how do we find A and B? One way of doing that is to have 1 node that is always well known, you can always find, and then attach relationship to that. And you can do that by this, attach things to the reference node. Okay, so why should we use a graph database? And one very nice feature, there's no concept of join. And if you just have to remember one thing from this speech is what graph database is for, it's really optimized for fast retrieval of relationships. And more important, it doesn't matter what data size you have. The traversal speed will always remain the same. And it doesn't even matter the depth of traversals. If you go 100 friends of friends of friends, we'll have the same traversal speed. And just, I mean, it's often silly to talk about performance, but just to give a rough impression what sort of performance you talk about, you can get sort of 1 to 2 million relationship a second, at least in the Java library. Okay, here is an example of traversing several relationships. It's not much difference, and then you can say where you want to stop. So friends of friends of friends of friends. And there's no concept of foreign keys. It's built in. And if you establish a link between A and B, there's actually no need to establish a link from B to A. You just have to keep in mind the direction of the relationship. And you can see here, you created a relationship, and then each relationship has a start node and end node. And here is how you can find that relationship. This rel just take the first relationship found, navigating incoming relationship of type friends, and then it finds this relationship. And you can go our way as well. And one very nice thing about graph database, they are very expressive things. And you probably use graphs all the time. For example, when you write things on the whiteboard and try to describe things, you do domain modeling. You might write something like this to write a blog application. And this is a graph. And to map that to the graph database, you don't have to do anything, basically. This is what it looks like in the database, just using a GAMP to visualize what the database looks like. And another nice thing is schemaless. So you can add any nodes, properties, relationship anytime you like. You might think that's going to be chaos. You don't know what the database, what to expect, what it contains. But instead, what you do when you program the graph database, you create self-describing structures. It's nothing strange, really. That's what you do in whiteboard as well. You put labels on relationships and nodes to describe your data. You do the same thing in database. For example, you can have a property, type or class or something, have some sort of meaning, telling that this node is a person. And that's what my wrapper does. It actually tells that this also a Ruby class. So it can be wrapped to Ruby class. But there are many different ways of doing this. You can have a meaning in the relationship instead, or you can have one node that has a meaning of things. And as an example of what the database can look like, here's the delivering products to customers. And here's the reference node. And for some reason, we wanted to aggregate data, for example, what has been delivered each day, do some statistic things, for example, in this node. And then we can find very easily all shippings that happened on a certain day. So this is basically a hash table that we implemented in the graph database. And product trees is, of course, very easy to do as well, to build up structures. So doing domain modeling in a graph database is really great fun. OK, so if you download Neo4j, you got an alternative how to use it. It comes in two flavors. First, there's the embedded database. It's very easy to install because it runs in the same process as your application, but can only be run from JVM languages on the JVM virtual machine. And of course, it might be much faster because you don't have to serialize data over the wire. You have direct access to the database. And you also have full access to the API, full control over the transactions. And the other alternative, if you are in a language that doesn't exist on the JVM, is to use the REST API. And then you install it like a more normal database, as a standalone component. And one nice thing, there is actually a Heroku add-on you can use to get it up very quickly. OK, here's my Ruby wrap. And it consists of 3 layers. First, a very simple mapping to the Java to make it feel nicer to work with. I mean, the next layer is a mapping, how to map things to Ruby classes. And then I got another layer on top of that, another game that I use the Rails Active Record API, implemented a subset of that. So it's easy to use Neo4j game in the Rails ecosystem. And quite many games work out of the box. So it's very, very easy to install the database. All you have to do is make sure you're running JRuby, install the game, and then off you go. You can just require it, and it will start automatically. So there's nothing else you have to deal with. An example of just using the lower layer, the core, then you use the Neo4j as a graph database. You're not interested in this mapping to Ruby classes and things. Example of what you can use it for is for recommendation. So here is a problem. We got 4 users, and we have tweeted things with different tags. And we see that Alice follows Ted. And we want to know which user we should recommend Alice to follow based on similarities on tags. So should Alice follow Bob or Carol? Well, if you look at Carol, they just got one tag in common, it's Rails. And with Bob, we got 2. So probably it's more likely she should follow Bob. We have more things in similar. So how do we write that code to give that answer? Here's one way. We just navigate a relationship from Alice, outgoing use tags, and then we find Neo4j and Rails tags, 2 tags. We put it in an array, and we find Alice followers, and that's just one person, Ted. And then we go outgoing use tags, incoming use tag, and stop at F2. And then we come outgoing use tag, incoming use tag, we end up in those 2 users. And then we filter, only include those users there, and then we exclude people we already follow. And then we have those 2 users. Then we have those 2 users, we navigate the other direction. Friends, outgoing use tags. We go here and here and find the tags. For Bob, we find those 3 tags, and for Carol, we find those 2 tags, put them in an array, and compare that with Alice, and just use plain Ruby array set intersection method, and then return the one that has some max similar tags. But you can do it much simpler than this recommendation, because there's a language, pattern matching language. It's really nice to do. So instead of, you sort of declare a match here, going used tags, outgoing used tags, and then incoming used tags. And then you say, limit this, where Alice must not already follow the user. And then you return the user, and you count all those things here that matched, and you order it, and then you have the same result. And also written a Ruby DSL for that. If you don't want to write queries as a string, you can use a bit nicer Ruby syntax. Does the same thing as up there. And there's also an online tool you can play around with those queries and visualize the query results. Okay, and the next game, if you're interested in mapping these persisting classes and things to the graph database, you can use this game. It works like this. If you create new objects of that type, it will add an extra property, a class name. So each time that node is loaded, it checks this property and wraps that node in a Ruby object. And then you also have a convenient accessor method, so you can set an expectation, what you expect, what sort of properties normally exist on that node. And you can also map a relationship in the same way. So you create an accessor method, friends, that navigate outgoing relationship. And then you can use that for both creating new relationships and finding relationships. And you can also map different directions. Let's say we have two classes. We have a relationship. We have actors and movies. And we want to declare an outgoing relationship acted in to the movie. But we want to navigate the other way as well, from movies to actor. And they say we want to use the same relationship acted in here, but the opposite direction. And we want to create an accessor method for navigating that direction. Yeah, you can also have declare types. So you always will always be a fixed num for the type, if you want. How do I find things? Yeah, as I said, first method is to attach things to reference node, and then you just traverse. And there's a slight variation on that theme. It's often a very good thing to introduce a lot of relationships. You get usually better performance the more relationships you use. Here, example, you can add. You don't want all nodes hanging under the reference node, for example. And you can create in-graph index, for example, doing search trees like this. It's not often needed, but sometimes you need to do that to speed it up. And Neo4j comes included with a LUCENE document database that's extremely good at searching for text. And to declare a LUCENE index, all you have to do is to tell what sort of LUCENE index you want. And then you can use the LUCENE query syntax to find things. And finally, got the Neo4j game that you can use if you want to use it together with Rails. So I implemented a lot of active record methods or active model methods. Yeah, inheritance works like you would expect. I can just give you some time to parse this in your head. Got the vehicle and inherited cars. And then you can, we're actually using LUCENE queries here. And it still works, returns with like correct things. And then I done a little extension to this, and the use case was this, that I wanted to find all instances of a class. And Neo4j has something called commit hooks. And I use that to create structures. I listen to properties. And if I just write this rule all, by default, it will listen to the class name property. And if I create a new person, then it will create a structure like that from a reference node. If this node doesn't already exist, it will create it. If it does exist, we'll just use that and add another all relationship to the newly created object. And then you can find all instances. Just find the node that represent the class and traverse all outgoing relationships very quickly. And but also support aggregation. For example, you want to find how many instances of that class exist. Then you can put this data up here, or actually any sort of function that get updated every time you change a node. And then you can also combine those rules to narrow down the search result. So here we got two rules here, and we got added some constraints that not only that the class name must match, but also some other properties must match to create this type of relationship. And then we can add all those together to narrow down the scope, and together with CYPHER DSL, we can do some interesting queries. And then it will create graph structure, something like this, one for each class, and then we create this special relationship, and then we can navigate this by the CYPHER DSL. Okay, the future of graph databases. If you look at the Neo4j graph database, it's been around for around 10 years in production, but I don't think it's till the last 5 years it's really taken off, become very popular. And I guess the reason is that the data these days is much more connected than it used to be. It's hard to find application that lives in isolation. You have to talk to a lot of external services. And I think there's a trend that data is just getting more messy and messy. And that's also a challenge, because it's very hard to index data that is messy. And one solution is that to rely on pattern matching, like I described here, navigating relationships instead. And that also allows you to do very intelligent search. You can, for example, find a search result that's just relevant for one particular user under very particular circumstances. But I also think it's quite unexplored technology. There's a lot of things you can do, because the node property relationship is such a general building blocks. You can make it into any type of database, more or less. Just this rules is something we invented. Other example of what we have is multi-tenancy. You can split up the graph database in several subgraphs. We do that by having several reference nodes. And we've also got versioning support. So you can rewind and forward changes in the database. You also do that by adding more relationships. And there's also open source project for doing spatial searches using the graph database. So it's a lot of possibilities for this type of database. And I think that's, oh, I had this last slide. Battery. It was just links. Any questions? Do I have time for questions? Yeah, it's quite a rich ecosystem. Yeah.
It's like a canonical example, like problem which do you solve with web database.
Pardon?
A canonical example of a problem.
A typical, yeah, I mean, one obvious thing I think you all think of is social networks, recommendation things, but it's been in very various domains, for fraud detection, anything where the relationships is really the critical thing in your application, where it really contains the knowledge of things. That's where you have use of that. But sometimes you don't have a choice. People building their own sort of graph database because they have to traverse things. So, yeah. Yeah.
My question will be quite simple. How about memory consumption and scaling?
Yeah, I haven't talked anything about scaling, but where you can run this in a cluster. I have not used it. We just played around with it, and they used Zookeeper to have the master election and things like that. I think they recently threw that out to simplify the setup. So it is, I mean, you can't use like hundreds of nodes, but you can use quite many. Yeah.
From the perspective of the cap theorem, what does Neo4j sacrifice? Consistency?
It has, I forgot to sell that. It has real ACID transaction, which is very unusual. Yeah, it's of course much harder to scale with a graph to hundreds of nodes, but yeah. Yeah. Yeah, thank you very much.